That's my cue. That's how we start. Welcome to the virtual night sky version of October the 20th in 2021. Thank you guys for joining us tonight. Hey, we have a really good show for you tonight, and that music is appropriate because we're going to try to shake things up a little bit. My name is Rick Alling, and I'm going to be your host. And I'm going to just describe a little bit about what we're going to do and introduce some of the players that participate in the background and help make these programs very successful. So first of all, the introduction. So Meg Hufford is here. She's a colleague of mine. Both of us handle outreach programming in buildings. So we are about public coming to us on the ASU campus. And we haven't been doing that lately. So even now with COVID, we haven't opened up to the public yet, but we will. And so we're looking forward to, after the first of the year, having visitors back in our building. And that's where we really shine. And that's really great. We started these virtual night skies as a way to just kind of keep in touch with people and do this as a virtual version during COVID. And it's become really quite successful. So we're glad for that. Kim Baptista is the one that actually puts the web mastering together, and her mastery in getting this thing organized and getting it communicated has been absolutely valuable over the last year and a half as we've been doing this program. So Kim is with us tonight. You'll hear from her afterwards too. There will be a little survey that goes out a couple of days after the program, and I'm going to say it now, I'll say it again at the end. We really use comments very seriously. So I'm going to kind of invite you to sort of participate in the survey and make sure you sort of keep us on track and let us know what you want to hear about in the future as well. One of our new staff members is Alicia Hyatt. You'll remember her as a student, and now she's here helping us out in more staff capacity. And so she will be kind of helping work with some upcoming events at the end of the program, and she's monitoring questions as we go. And Alex Blanche is a student in our program. He's been working as a docent, and he's training in the Marston Theater for when we do reopen for the public. And he's here. He'll be also working questions in the background, and you'll hear from him a bit later. Tonight is a little bit different. We actually are going to talk about earthquakes, and it's earth science, and there's a good reason for that. Virtual night sky was conceived of a way for us to sort of like do programming where we look at the evening sky and we talk about stars and constellation, all that stuff, and we do that. And tonight we're going to talk about Venus and how to watch Venus for the next couple of months. But we are part of the School of Earth and Space Exploration. And at ASU, we do things a little bit differently than other places. Our astronomers and our astrophysics people are actually in the same school as the geophysics people and the geologists in our program. And so we work together very closely. There's lots of links between those two disciplines that make us extra special. And it gives us an opportunity to tap resources that we wouldn't otherwise have. And just this time of year, there is a thing called the National Shakeout, and it's about earthquake awareness. And we thought we would have a guest tonight that helps us take care of that. I will introduce Ramona in just a little bit. Some housekeeping. This is a webinar format, and so you can't chat with us, but you can activate your question and answer button, and anytime you want, you can ask a question, especially, or make a comment, or sort of engage with us that way. And we do encourage that. So questions are answered in the background as they go along, but we also save questions that will be presented in front of everybody. And so at the end of the sections of the program, if you have a question, put it in there, and we'll get to it. We'll bring it in front of the audience as well. So that's good. We're also going to do some polling, so get ready for that. If you've never done that before, there's a little, you'll see. We're going to launch some polling questions and ask you to interact that way as well. We do closed captioning, and so you might see it on your screen, and you're in charge of that. So if you want closed captioning, you can leave it there. If you don't really want it on your screen, then you can turn it off. We do that because it's easier for us to move these programs into YouTube after the program. So with all that kind of housekeeping out of the way and everything kind of under control here, it's really my pleasure to have as a special guest tonight Dr. Ramona Aerosmith. Aerosmith. Dr. Aerosmith has been a leader in our program for quite some time. He was an interim director for a while. He's the associate director of the School of Earth and Space Exploration, in charge of operations. And so we interact in a lot of ways, from the business end to the presentation and science end. And it's been fun to work with Ramon for a long time. And he also happens to be the go-to guy when earthquakes happen. And so I don't know if you've noticed this, but the news will pick up on an earthquake and it happened last night and all that stuff, and the phone starts ringing and they're trying to get a Ramon to get on the air and kind of explain what's going on and why this is important. So with National Shakeout, we'll talk to you about that a little bit later, but tonight is about earthquakes. And so Ramon's going to be on to do his presentation in a second, but we're going to do things a little bit differently. We're going to start with a poll. We're going to get you to interact with right now, and we want to know from our audience, have you ever been in an earthquake? And so you'll see it come up, and there's a way for you to interact with this. Go ahead and just start registering. Have you ever been in an earthquake?
There's also a second question attached to this that says, how did you experience it, which goes through all of these different levels of feeling. So those are lumped in together. So you'll be answering two questions.
Excellent. So we're going to learn a lot about the audience that we're going to be talking to tonight about earthquakes by seeing. This is something that I think I guess, if you've been around long enough, almost everybody's experienced an earthquake, as would be my guess. I remember it as a child. I lived in Denver for a little bit. We had the shakes every once in a while. I remember that.
Yeah, it looks like 80% of the group has felt an earthquake, and mostly it was modest shaking.
Oh yeah, so I'm actually not seeing. Let me scroll down here. I'm just kind of controlling my own poll. Yep. So most of it was just sort of they maybe were aware earthquake happened, but they didn't really feel it, right? I guess that happens to a lot of us. You wake up in the morning and read in the paper there was an earthquake last night. I think really, if you're driving, you're not going to feel like a mild earthquake, right?
Well, sometimes people feel it and they think their car is getting a flat tire or something.
Oh, okay.
So they don't associate it with the actual earthquake. But it's also, maybe most people here have lived in Arizona for a long time, and that's one of the messages I'll have for tonight is there's not a lot of big earthquakes in Arizona, but we should still care about them because we travel, you know, around the world, and California, which is our neighbor, has big earthquakes.
Excellent. Well, I am going to turn it over to you, Ramon. Thank you very much for joining us tonight.
Right.
And I can't wait to hear about earthquakes and shaking things up.
Let's see if I can make sure I share my presentation here. So what we're learning with our little poll there is that let's just share the results here so maybe people can see it. But 80% of the group have felt an earthquake or been in an earthquake, and mostly, you know, weak 19%, light 17%, moderate 19%. So that's pretty typical. And what we're feeling in an earthquake we call intensity. So that's the shaking in an earthquake at a point, and it can vary with position. So it's kind of like in the case of a light, no matter the wattage, the further away you are, the dimmer the light. And so we can measure this intensity in a kind of standard way, and that's what's shown this table here. And this is something called the Mercalli intensity scale, and we usually use these Roman numerals with it. And this was developed originally by an Italian natural scientist named Giuseppe Mercalli. So he worked on earthquakes and volcanoes. So that's intensity. And let's just look. So there was an earthquake in 1989. Some people call it the World Series earthquake, but it actually was called the Loma Prieta earthquake. But here you can see this picture shows the people in Candlestick Park after the earthquake disrupted the Game 3 of the World Series. That was between the Oakland A's and San Francisco Giants on October 17th, 1989. So I showed this for a couple reasons. One is I was actually in this earthquake in the Bay Area and the peninsula and had pretty strong shaking. I had a 7 shaking. If we go back to our thing here, you know, I was certainly frightened. Furniture was overturned. Some of the buildings where we were damaged. But if you look at the map on the right, you can see how it was felt widely in the San Francisco Bay Area, all the dots and triangles are different sensors that were used, and also reports from people of what they felt. The other reason why I'm showing this is that it's why today, or this period, is the time for the shakeout. So it was really initiated by the memory of the Loma Prieta earthquake. And so that's why we have it this time of year. And it's baseball season. So key issues for earthquakes are the source, path, and site. So the source of the earthquake is the breakage along the fault. When the fault slips, it generates seismic waves. Then the path is the path of the seismic waves. How do those waves move away from that source through the earth? And so it's kind of like ripples on the surface of a water body. Not exactly, but kind of that same way. They move away, just like sound moves through the air. These are sound waves moving through rock. And then the site is the conditions at the site and the structure there that control the intensity. So in this diagram from California, from the Loma Prieta earthquake, you can see the black line shows the source. So that's the part of the San Andreas Fault that slipped. And that length and depth is what controls the magnitude, which we'll talk about in a second. But you can see that it goes down with distance, but it's not uniform. You see that in the sort of some of the lowland areas in these basins, there's a little bit of enhanced shaking, this kind of exaggeration of the ground motions that we see in some of these basins. So things are a little bit more complicated, but in general, as we move away from the earthquake, the intensity decreases. And so in contrast to intensity, the magnitude is the measure of energy in an earthquake, just like the wattage of a light bulb, 100 watts versus 50 watts. And on the right side, we could, instead of wattage, we might do kilograms of TNT or Newton meters. And then on the left, we have this kind of convenient scale, sort of, 2 to about, well, for, 0 or even smaller for very small earthquakes, up to about 9 or slightly larger. Sometimes we talk about the Richter scale. It's named for an early seismologist, but or the moment magnitude scale is something we're sort of, our intuition based on history, we may say, okay, well, yeah, so Loma Prieta was a 6.9. There have been bigger earthquakes, and what this also shows with the widening of this orange sort of part of the figure is the smaller the earthquake is, the more there are per year. So there are always earthquakes, but many of them are very, very small. We don't feel them. And so, the magnitude, this energy depends on the length and width of the fault that breaks. And so along with the earthquakes, we can think about energy that released by other things we might be more familiar with. So like a lightning bolt is around a magnitude 3, or atomic bomb explosions can be, Hiroshima was around 6. The world's largest nuclear test was almost an 8. And some volcanic eruptions can have the same energy as great earthquakes. So now let's come to Arizona. So most, but not all earthquakes in Arizona have occurred actually in areas surrounding Arizona. So here's a map of Arizona and California, and you see most of the orange circles, which are color coded by their magnitude, and they're located where the sort of the middle of the fault where it broke. You see most of them are in California. So Arizona doesn't have a lot of earthquakes, but we do, and they're important to be aware of. We're not on the plate boundary, so that's what's driving a lot of the earthquakes. It's kind of the earthquake engine, is the shearing of in this case, it's the San Andreas Fault System. That's the boundary between the Pacific and North American plates. And so that's another reason why California has a lot of earthquakes and Arizona doesn't. But that boundary isn't really sharp, or it's fairly sharp. But if you look at these arrows, so these arrows, if you start in the lower left, if an arrow is the length of this pink one, it would be about 25 millimeters a year relative to North America, stable North America, so further to the east even than this map. And so you see the arrows in California are really going fast, like almost 50 millimeters a year to the northwest. So that's the Pacific plate. But as you cross the San Andreas, which are these red and white lines, you see the rates of the length of the arrows goes down. These are velocity vectors measured by GPS systems. And so when you get to Arizona, you see the arrows are really small, but they actually still get smaller as you go across Arizona. So we do have stretching of Arizona, 1 to 2 millimeters a year. That's about 20 times slower than the stretching and shearing in California, but it still drives earthquakes. So we can think of that stretching as kind of like this engine, where the stretching and shearing is the hand that's pulling the spring attached to this brick on sandpaper. And so the bottom of the brick is kind of like the fault surface that slips. And so the hand, let's go back so we can see that one more time. So the hand is pulling steadily. That's the plate tectonic motion. The spring is the springing or loading up of the Earth's crust. And you see once the strength is exceeded, it slips. And that's the earthquake. And that's what releases the energy. So a fault is an interface along which there's relative motion. And when we stretch the crust, we get a fault like this. So this is called a normal fault. It's not a typical fault. It's just one that has that accommodates stretching as opposed to contraction. And this is the kind of fault we have in Arizona in general. But you can have ones that accommodate shortening, and that would be called a reverse fault, or ones that accommodate more relative horizontal motion, we call strike slip fault, and that's what the San Andreas is. But as you saw from those arrows that are across Arizona, the ones in the west are longer than the ones in the east. So we're stretching Arizona at 1 millimeter or 2 per year. And that has to be released by an earthquake. Just like the hand is moving, the spring stretches, and finally the brick has to slip. So here's some important historic Arizona earthquakes. This is from the Arizona Geological Survey, and it was up to 2000. So there's a few since then that I'll mention. But you can see the map here, and you see these dots go with the magnitudes. So we see that, of course, there's earthquakes in California along the southern San Andreas system, but there have been earthquakes, especially in that zone around Flagstaff, near Prescott, and then between Flagstaff and Grand Canyon Village. And these would be since 1830, as we see on the upper right, when we had a good record of what had happened. And where we see the Roman numeral here in this upper right table is kind of peak intensity. And then when we get a number is when we figured out the magnitude. So we really only have good magnitudes for the latter earthquakes. So I'm going to show a few of these, some examples. And the first one we're going to start with is the one down actually in Mexico, but it's Arizona's most famous earthquake that occurred in 1887. And that's this one. It was the 3rd of May. It was a magnitude 7.5 earthquake. It was huge. And it was along this fault called the Pitaycachi Fault in Sonora. So it's here in this area just south of the Arizona, New Mexico intersection in Mexico. And it was in a place called the San Bernardino Valley on the west side of the Sierra Madre. And the most damage occurred in this Bavispe town. And this just is a tabulation of what happened. So buildings swayed in Phoenix. Tucson houses were cracked and some chimneys fell. Yuma, water sloshed in canals. And Albuquerque, where I'm from, people felt seasick. In Charleston, and AT means Arizona territory, the walls of the saloon did a 2-step and the floor did a shimmy. So it's kind of appropriate maybe. And the quake probably hastened that ghost town's demise. And so, as I said, 51 people died in northern Arizona, in northern Sonora, and most of them were just in this town, Bavispe, sadly. And I wanted, as I go, some of these slides came from Steve Semkin, so I do want to thank him. And so this earthquake was also interesting because it had impressive manifestation of the processes of the faulting. And so you see this picture here of these two vaqueros next to this fault scarp that formed. It was 14 feet high, 4 meters high. But the other thing that was quite interesting was it was an opportunity for an international scientific expedition and meeting. So in Tombstone, George Emery Goodfellow and photographer Camilla Sidney Fly, who took these pictures, were there, and they headed down to see what happened. And at the same time, a Mexican scientific expedition led by Jose Guadalupe Aguilera Serrano was dispatched from Hermosillo, and they met. And that's what this picture in the lower right shows, is them standing on top of the ground rupture discussing their observations. Other earthquakes that have occurred in Arizona were around Flagstaff. Our kind of famous 20th century earthquakes were these three that occurred 1906, 1910, and 1912 around Flagstaff. And they were around magnitude 6, and peak intensities were Roman numeral 7. So a lot of shaking. And you know, if you imagine if these earthquakes recurred, there would be a lot of damage. So in January 1906, chimneys were shaken down, crockery fell, clocks were stopped, school children were in a panic. In 1910, numerous severe shocks were experienced by a dam building crew working north of the San Francisco peaks. And also a lot of the lumbering that was occurring in the San Francisco peaks was really disrupted by boulders that were shaken loose. And in 1912, this little scratch of a seismogram was actually recorded in Denver as the sort of long distance shaking from that earthquake. So this map on the right shows the topography of this part of Arizona between Phoenix and Flagstaff. And these orange and yellow lines are the faults that we know of that have been active in the recent geologic past. So we know these faults are there, and they influence the topography to some degree, and they accommodate that stretching of Arizona. So another earthquake that maybe it's more recent that people might have felt was on the 4th of April 2010. It was also in Mexico, but it was felt strongly in Arizona. It was about 211 miles away, or 340 kilometers away, and it occurred near Mexicali. And here's the map of what people reported that they felt. So more than 77,000 people went online to show what they felt. And you can see here for Phoenix area that it was weakly felt, but a lot of people felt it. And then in Mexico, of course, where the source was, it was strongly felt. Here's actually a swimming pool that shows the shaking. So this is the security camera from the swimming pool in Mexicali, and it was pretty close. So you see things are kind of calm, but watch, you know, there's a little bit of breeze. This is actually Easter Sunday morning, so some people were having brunch. Now we start to see the pool move a little bit. Is everyone watching? No, just get ready. The shaking is going to start kind of calmly in just a few waves, but now we see the shaking begin. And it shakes. And then the waves become stronger as the waves coming along their surface come in. The surface waves really shake a fair amount, and it's even more vigorous. So this is the camera shaking on its pole, but then you see that the pool is going to get whipped into a froth. And sometimes these waves in pools are called a seiche. So the entire pool water is moving back and forth. And now the earthquake shaking is diminished, but the waves in the pool are still going strong. Look at that. So small tsunami in Mexicali. So here's another one. This is earmuffs. So if you have young people or people who don't want to hear a gentle swear, put some earmuffs over their head. But this is a couple of young adults are traveling in northern Mexico, not far away from the earthquake, and they felt the earthquake from their car, and they see the dust on the mountain.
Oh my god.
Holy shit.
That was gnarly.
No, that was really scary.
We should call your dad. I wonder if the house is okay.
Oh my.
Yeah, I couldn't figure out the road was messed up, and then I realized the other cars were doing it too. Yeah, and then I'm looking over there, and it's
That was really
That
weird.
was intense. Oh my god.
As you can see, the people pulled over because they were really freaked out. Again, they thought they had a flat tire. But what's happened is that the dust coming from the heavy shaking of the mountains and all the rocks have slid down, and this massive amount of dust has been activated or moved. So an interesting, strong effect of this eyewitness experience of that earthquake. So here's our team here at ASU worked with some of our colleagues also from from Mexico, from CICESE, and also UC Davis to do airborne laser scanning of the rupture. So you see this topography here with illumination from the upper right. The light is shining, and you see the reflection of this artificial illumination off the fault scarps that formed in that earthquake. And here's two colleagues standing on the rupture, and before the earthquake, they would have been standing right next to each other with their feet touching. So the ground slid horizontally, but also vertically. So when you think about Phoenix, we did some work also with our colleagues in the Fulton Schools of Engineering, Professor Kavazanjian and Simon Gannat, and we worked on what is the updated kind of source characterization for Phoenix for possible earthquakes. And you can see there are a few faults that, and these blue lines show 50 kilometers and 100 kilometers from Scottsdale. So we have a few faults around Phoenix, but they're not very long. So remember, I said that length is what is an indicator of expected magnitude. And they also have very, very low slip rates, which means that when they would have earthquake, it would be very uncommon. So long times between earthquakes. So we shouldn't worry, but they are there, and you see the orientation is again consistent with that east-west stretching of Arizona. So there was an earthquake that occurred near Phoenix that was kind of got people's attention. It was in November 30th, 2014. It was the biggest one, was a 4.7. And this is kind of around the Sunset Rest area if people drive from Phoenix to Flagstaff on the I-17. And there were a couple of foreshocks, and then the main shock was a 4.7. And so here it was recorded at ASU by our seismology colleagues, John West and Professor Ed Garnero. And you can see this is the ground motions that were recorded in the bottom of one of the buildings. And you see the foreshock is pretty small shaking, but that main shock came in 11:30 p.m. And, we had the first onset of the P waves, the body waves come in, and then this stronger motion as we get the waves coming on the Earth's surface. And then there was an aftershock about 10 minutes later. It was a magnitude 4, somewhat smaller ground motions. And so what I thought was really impressive about this earthquake was that it was weakly felt, but by 4.5 million people. And so when you want to get people's attention about earthquakes, this is a good way to do it. So it's small enough to not cause a lot of damage, but definitely big enough to be felt widely and to remind people that Arizona earthquakes do occur. And a few saguaros may have been damaged. So this is, we can rebuild our sort of Phoenix damage from the earthquake. So just to start to sum up, this is the seismic hazard for the US as produced by the US Geological Survey. And so you can see redder is higher hazard. So definitely the plate boundary zones of the Western US, as well as some of the plate interior zones, like part of the Basin and Range here, Wasatch Front into Yellowstone area, and then some places in the mid-continent, as well as, of course, Alaska and its plate boundary, are where the highest hazards are. So we do have green and some blue and yellow, so moderate hazards in Arizona. It's not as low as other parts of the US, but that's modest. So in a way, I also like to say that one of our biggest worries is an earthquake in Southern California that would we might literally feel in Arizona, but also figuratively feel in the sense of our social connections to California, but also, people have been hearing maybe about the ports of Long Beach and Los Angeles. So much freight moves from California through Arizona to the rest of the US, and many of those faults would cut those train lines, those rail lines and the highways, I-10, I-8, also a lot of telecommunications. So we need to worry about it. Also water. Just looking quickly at global seismic hazard, we can see where expected earthquakes will be in a relative sense. So dominated by plate boundaries and zones of, especially in southern Eurasia, zones of convergence between continental fragments and the main Eurasian continent. And people say, oh, there's been just more earthquakes, something's going on. And so if you look actually at time versus magnitude on the upper plot, you see that there's been steady, semi-steady, but kind of pulsatory history of earthquakes. Actually, in the 1960s was a really crazy time with a number of really huge earthquakes. And we had some big ones in the 2000s. But what has been changing is what's in the lower diagram is people on the earth. So our populations are growing. We're more and more in hazard. And that's what we really need to worry about. We need to care about our fellow people. Also, the global economy is more exposed to these natural phenomena of earthquakes. So what to do, the idea of shakeout is to protect yourself during an earthquake. And if there is one, you want to drop, cover, and hold on. So don't stand in a doorway because the door could slam on you, slam on your fingers. Just get under something, if possible, that's strong, and hold on and ride it out, and then look for your loved ones and work to recover. So if you are interested, you can join up for the Great Shakeout. And, it's 46,000 people from Arizona have already signed up. But, people can join in, and, you can say, oh, well, you just told me that Arizona doesn't have a lot of earthquakes. And it's true, but I told you there are some. But again, people travel, when if you're in California or another part of the world and there's an earthquake. So you want to be aware, be ready. And in general, it's just, like the pandemic has occurred and reminded us, we need to be organized, communicate with our loved ones, and be prepared in general to take care of ourselves in case of any kind of a problem. So with that, I'm going to stop, and I'm certainly available and happy to keep talking. I could, I'm a professor, right? So I could talk forever about earthquakes, but I want to take a break and
Thank you.
if there's some questions.
I think there will be some questions, and we'll get ready for that. And while we have you and while we have your attention, we also know that ASU participates in a lot of missions to planetary surfaces, and we do a lot of work out in the solar system. And I was just going to ask you if you participate in, or you're aware of missions that include seismometers and those kinds of things that we're like trying to learn about earthquakes in the interiors of other planets.
Well, I'm not working so much in planetary seismology. I tend to stick to the Earth, but I love, learning about earthquakes everywhere. And this is from the InSight mission that is on Mars right now, and it has a seismometer. And so you can see, this seismogram that came from Mars. This was, I think, a magnitude 4.7. And then on the lower right here, you can see the location of the lander, and then these epicenters from earthquakes on Mars. And off on the far right is Tharsis, one of the big volcanoes. So it wasn't coming from there, but maybe from some of the faults. So Mars is not nearly as tectonically active as the Earth, but it has a few, cracks and active stretching that must be manifest as earthquakes.
Was that expected? Is that a big surprise that there's earthquakes on Mars?
No, I
Would we
think
think that there would be?
people thought they would happen, and
Uh-huh.
we, of course, we're interested in the source, in those faults on Mars. But what these really do is give us a probe of the Martian interior. And so the path is what most people care about, is how did the waves move through the interior of Mars? And what does that tell us about the kind of larger scale structure of Mars?
And just real quick, and then we'll wrap that. We'll go to some audience questions. But do we have enough sensors on Mars to know something about the interior? I mean, do you have to have things in multiple places, or is there enough to work?
Well, it's hard with one seismometer, but very clever seismologists have worked to get the most out of these. So they have a sense of where the earthquakes occurred. But yeah, they can look, as you look at different distances, the waves will go deeper and sample different levels of the Martian interior. And they have very good timing, so they can basically estimate the seismic velocities of the Martian interior and then turn that into interpretations about what's happening on Mars.
Excellent. I think that's really, I started introducing you by talking about geology and planetary sciences and the engineering that goes into that. And that's that relationship, isn't it? So where we learn from what we can learn on Earth, and we apply these things to other places.
Absolutely.
That's the place. I'm going to invite Alex and Alicia to just jump in and help us with some questions.
All right. I should say, while they're jumping in, there are seismometers on the moon, and they have been there for a long time.
okay.
So that was part
Moon-
of the Apollo mission, was lunar seismology, and Professor Garnero has worked on them.
And the moonquakes and Marsquakes, is that what we call them? I guess
Yep,
it is.
that's
Okay.
right.
Okay, good. Alex.
All right. Yeah, we have a bunch of good questions. So this first one's from Howard. They asked, does the magnitude of an earthquake depend on the physical properties of the rock? Say more malleable rock tends to produce lower magnitude earthquakes.
Yeah, it does, although it's not as important as the size of the fault that breaks. But a stiffer rock will, when it snaps, it'll produce more seismic energy than a less stiff rock.
Okay, and then another question. Joy asks, do earthquakes on other celestial bodies work exactly like the ones on Earth, or are there any differences?
We think they work similarly. These are frictional processes, so you're sort of pushing one side against the other, like the brick analogy, and you're loading them up somehow, either by plate tectonic motion or more just body forces or tidal forces. So something's driving it, and then you have to overcome the strength, and it will slip, and then it produces those seismic waves.
All right, thank you. And I guess this is kind of just one more question, just kind of related. Do higher magnitude earthquakes, this is also from Howard, do higher magnitude earthquakes require a longer time to reach the breaking point, that snapping point, or do they just not have those smaller shakes to act as a catharsis?
Good question. In general, yeah, if you need, it's kind of like how fast is the hand moving? And so, if you have if you have a steadily moving hand, then you're going to take more time to sort of charge up that piece of the fault that might ultimately break in a large earthquake. But it's kind of complicated because our analogy is just one spring and one brick, but you can imagine a whole network of springs and bricks sort of attached together, and you pull on them, and so it's kind of like so the earthquakes can kind of talk to each other as well. So it's a little bit tricky to answer that question in a simple way.
All right, well, thank you so much. That's the questions we have right now.
Excellent.
Back to you, Rick.
Thank you, Alex. And so pre-COVID, when we were kind of operating out of the building, we would have these annual events in the Marston Theater, and Ramon and Steve, you heard about him, and Ed Granero, and they would do these kind of programs in the theater. We'll look forward to doing that next year, and so there's always something to learn. There's always new activity, new earthquakes, and new technology out there. So it's been kind of fun to follow. And once a year, we can just kind of acknowledge that earthquakes are something we should just be aware of, and for good reason. So thank you, Ramon, very, very much for your assistance tonight. I appreciate it.
My pleasure. Thanks for the invitation, and thanks to you and the team for hosting and driving. Okay,
thank you. All right, I'm going to kind of get us into the night sky or space. Let's go sort of visit space for a moment here. I'm going to share screen. And what I'm doing is I'm using some of the technology from, let me see if I got everything set up right. I'm using some of the technology from the Marston Theater, and we're going to fly around. Sometimes I like to call sections like this Planet Watch, but there's something going on, especially with Venus, that I thought I wanted to kind of point out to you. This is very, very observable, and that's one of our goals, is to make sure that we give you something to look at either tonight, and you can actually go out and check this out tonight, or over the course of the next several weeks, because Venus is doing something special. You see, I'm just kind of like flying around the solar system just a little bit. Let me get it a little bit better organized, and up here I can put on the orbits of the planets in the solar system. There you have your sun. The four inner rocky planets are in the fore part of the screen, and the gas giants out there. Let me size those up a little bit. Sometimes people don't like it when you sort of like you cheat the scale of things, but I like to do it because it gives you a little bit better look at what's going on. And so tonight, what I wanted to share with you is sort of information about what you can see in the night sky. And tonight we're going to start with this big view of all the planets, and then I'm going to spend a lot of time talking about Venus because it's actually doing some things right now that are noteworthy, and things going on in space and things you can look at home. It looks like I have moved way out of to scales of time, so I'm going to go back to tonight. And so this is actually the relative locations of all the planets right now, just even as we speak. I just put the push the button that says now, and that means this is where things are now. You can see the planet in that blue orbit, the third one from the sun. That's the Earth. With the yellow orbit inside it is Venus. Mercury is the next one in, and of course you can see the big, huge giants, Jupiter and Saturn off to the side. If you were to draw them, and get out back a little bit, if you could just let me show you how this works. If we were to draw a line right through the Earth and the sun, just right across the screen here. So see how we do this, just right through there. Everything on this side of the line is visible in your evening sky. And so the sun has set and those things are available to us. Everything in the lower part over here is visible in the morning sky. And so there are some things going on there. Let me just zoom in real quick. I'm going to try to set up a really pretty picture of the scene here. So when we look to the south right now, I think it's a little cloudy right at the moment. Clouds are the wispy though, so they break up, they move around, and I am guessing that if you were to look right now, you would see right to left, you would see Jupiter and Saturn either towards the south or a little tiny bit east of south, and they'll be in the night sky. And then if it's not too late, if you're looking right now, you would see Venus just in the west, just at the horizon and going down. And so Venus is really sort of the subject of our program, the main part of our program, but I wanted to introduce you to the rest of these right now. So all of these objects are not just flying by, they're with us for a while. And so this will be the scene we've been watching for the last couple of months, and the scene that'll be available to us all the way through November and into December. Eventually, Venus is going to sink into the sunset, and I'll show you that in a moment. So let me sort of get these planets out of the way. And I wanted to just sort of like do a little setup where we're concentrating on the Earth and Venus all by themselves. And let me just sort of like do this and do this. I can get their orbits up, and I'm going to get like a little straight down view here. So here is the relative location of the Earth, Sun, and Venus right now. And the reason Venus is so prominent in our western sky right now, it never really gets that far away from the sun, but you can see we actually call this orientation, we call this the point of greatest elongation. What that means is that Venus is as angular distance, as far away from the sun as it can get. And you can sort of see that from these orbits. You can see if I just sort of like look right through the Earth and over to Venus, Venus can't move any further this way, right? It's on this sort of outer extent of its orbit. It's coming around here. It's moving faster than the Earth, so it's actually coming straight towards us right now. We're moving this way. And so over the next couple of weeks, what's going to happen in the western sky when you take a look, when you go out and look at this thing, it's going to look like Venus is kind of staying in the same place all the time. And people have been staring at Venus for thousands and thousands of years. And this is the special property of Venus that makes it noticeable. First, it's much brighter than the stars around it, and it doesn't seem to follow the rules. It doesn't, so it changes positions against the stars, but it locates itself about the same distance above the horizon at sunset for a long period of time. It just kind of hangs there, and it becomes an evening apparition, if you want, for a long period of time. It just sits there. It's very bright, very observable, and that's really the location it is right now. All right, so what's going to change? Well, I'm going to do this straight down. I'm just going to move these forward in time just a little bit, and so you'll see I'm moving forward to January the 8th. And you can see that they've moved themselves, Venus moving a little faster, Earth moving a little slower, and now they're in that position. We call this the inferior conjunction, or lower conjunction, some people call it. But that means that Venus is passing right between the Earth and the sun. That means we can't see it. Once it's lost in the sun's glare, once it gets close enough to the horizon right at sunset that you start to sort of like, it just sort of blends in with the glow of the sunlight, then it's gone for a little period of time. Let me move back again, and then I wanted to show you one more thing while we sort of have this view up here. I have just a little diagram that might show you what this looks like. This is sort of the Venus's orbit. So here's the Earth down here, and here's where Venus is right now. And you can see that when it's on this side of the sun, again, it's an evening thing. When it passes by and it goes over this way, it's a morning thing. And you can see how long it's up there. So 263 days. That's like 7.5 or 8 months that we see it as it appears in the western sky, and then moves all the way around, and then we'll get lost in the sunset, as I just demonstrated in a little bit. I'm going to, and then we're blinded, right? It's in the sun for about 8 days, and then we'll start seeing it as a morning object, and it'll do the same thing for almost 8.5 months. It'll be a morning object. It's kind of like floating through the sky. Then we'll lose it again behind the sun for about 50 days, and then the whole process starts over. From here, when we start to see it in the western sky until it goes all the way around and then starts over again, is about 19.5 months, a little bit over a year and a half for those sort of conjunctions, if you want to line up and everything to be right for us to see that. Let me just, I'm going to make the picture about 50% less, and I'm going to try to fly us in such a way that you can sort of see. I'm going to try to prove something to you here. I'm going to put my live solar system view right on the diagram here, and you can start to see how this works. So you see how the Earth is kind of like down by the Earth. Let me see if I can, I'm manipulating live here, so pardon me if it's just not quite lining up. Here it is, and you see Venus, and sort of like at that location on this particular outer part of that lobe where it's arrived at its greatest elongation. So what that means, because it's heading right for us in the racetrack in space, that means it's essentially going to look like it's stationary. It's just going to stay there for the next 6, 7, 8 weeks, and then it will it'll start to suddenly move down. Now, I'm going to show you one more thing in this big scale of things. Remember, I moved up to that conjunction. Let me show you this funny little Earth-Venus relationship. And so I'm going to do a 1 year of Venus movement. So it's going to go around once. There's a Venus year, but it moves faster than the Earth. So we're not at conjunction again a year later, right? In fact, we're kind of opposite each other. Let me do another one. I'll just keep doing this for a little bit. There's another Venus year, and the Earth is moving around. It turns out that there's actually this funny little relationship between the Earth and Venus, that for every 8 revolutions of Venus, the Earth does about 5, and it's not exact, right? We've just done 4 Venus rotations, and now we're at 2.5 Earth rotations. So you can sort of see this sort of 8 to 5 relationship, and so that means that when we see Venus in the western part of the sky, what's happening is we're sort of the process, what we get to see Venus doing in the western sky, repeats itself about every 5 years. In fact, Venus, as it moves across the western sky, let me just go down there. I'm going to show you. So as Venus moves across the western sky, it only does 4 things. All right, it just sort of has this particular movement because that's when it appears in our western sky. I can show you. Let me just get this set up a little bit. For those of you that have been watching for a long time, you've probably seen this before. What I'm going to do is kind of get us into the western part of the sky. What I want to do, I'm going to sort of like bring up my neighborhood. So here's the sky in my particular neighborhood, and got to go one more place here. I'm going to set up Venus so that it's in the sky, and this is when we started to see it appear in the sky, and this was last May. This happens to be May 19th. I'm going to turn on a little trail here. Watch what happens. I'm going to just kind of move through, and so what you're seeing here, you're going to see the location of Venus in the sky 20 minutes after sunset, and for a long period of time. I'm going to put a trail on. So in an evening, you don't see Venus moving like this. So this is time lapsed, if you want, where Venus is every evening for about 8 months. And you see, I mean, it never sets, right? I mean, it's always available right after sunset. Of course, it'll go down after that. But every single sunset you get to look at, it sort of like moves through the sky. Now watch this really cool thing. It's going to move up. That's it's going its greatest elongation, and then it's going to go down and get lost into the sun's glare right after that. So that shape that you're seeing on the screen here, this is the cool part. 5 years from now, this is going to do this again, right? And in the interim, there's going to be 3 other motions of Venus through the western part of the sky, and they're going to look very different. In fact, let me show you another one. We've got just a minute here, and then I'm going to turn you over to the other part of the team. I'm going to show you another one. This is the last time Venus actually sort of like moved through our western sky. Not the time we're watching now, but 19 and a half months ago. And see, look at that. Totally different characteristics. In this one, it's starting kind of in the west, moves a little to the south, and sweeps over to the north. The episode that we're in today, right, is part of that episode where it starts kind of towards the north, comes up, then moves almost directly towards the south, does a little loop-de-loop and in. So back in time, indigenous cultures in central America, in fact, the Mayans in particular, they revered Venus as some sort of special god, a war god, maybe somebody that would visit when it was time that they needed the extra powers to go to war and fight their battles. But it was also thought of as, you guys have ever heard of Kokopelli, right? Sort of the Kokopelli has been popularized over time, but the Kokopelli was actually a traveler. It was a merchant, and the travelers were very special in those days because they would move around place to place, northern Mexico, southern Mexico, down into Central America, back and forth, and they would actually sort of like carry information and goods and things like that that you otherwise couldn't get. And so Venus was also seen as this. And I can look at these particular things and know that Venus was revered as an object 1,000, 1,500 years ago in Central America, and you can actually watch this happening. And it's because Venus never gets very far away from the sun, and because Venus has this orbit, and for a great period of time, I think my chart said 263 days, it's in the western sky and does this big, huge sweeping movement across the sky over time. If you're an astute observer, you get to watch that and you get to see what's happening. Okay, that's really, I'm going to leave you with that. So I want you to sort of in the next couple of days go out and check out Jupiter and Saturn. Easy to see. They're the brightest things in the southern part of the sky. Jupiter brighter than Saturn. Right to left you see Jupiter, Saturn, and then way up over towards the western horizon, very bright Venus. It's going to be there. It's going to be stable. It's going to be in your night sky for the next 2, 3, 4 weeks. I'm sorry, 6 to 7 to 8 weeks. Somewhere in the middle of December, I suspect it will drop down behind the trees across the street from my house, and we'll just wait for it to do this again in 19 and a half months. So I'm going to turn the program over. Oh, one more thing I wanted to acknowledge tonight, because we can, of course. Tonight was a full moon, and Luna was out there watching, and Luna was sort of like watching the hunter moon. All of the moons are named, and it was a full moon tonight, and so I hope you watched that. And one of the special properties of the full moon is that it's that time of the month where the sun sets and the moon comes up exactly at the same time. It has to happen. Sun goes down in the west, moon comes up in the east, and because it's a full moon, the Earth is in the middle, and those two objects are opposite each other, and that's how we find it. And so I'm going to end there. I'm going to invite Alicia and Alex to give us a little update on some resources for you guys to use, and then also some current events, some stuff going on that you need to know about.
Thank you so much, Rick. Hello. So just recently, this Saturday, October 16th, just after 5:30 a.m., The Lucy mission launched in Florida, and it was on a Saturn V rocket. It was very exciting. And this is NASA's first mission to the Trojan asteroids. And so this is the mission patch for Lucy. And so I got this with some of my coworkers for running a virtual 5K, a NASA virtual 5K. So I thought that was interesting to share. But what I'm going to do right now is share my screen to talk more about this Lucy mission and to talk about current events. Alrighty. So for current events, like I mentioned, we have our Lucy mission. And if you are curious, yes, there were diamonds on this mission. And as I said, it launched just this Saturday. And we're really excited to go and take a look at these Trojan asteroids, because like I said, this is NASA's first mission. And very excitedly, ASU has an instrument on this spacecraft called LTES, which stands for the Lucy Thermal Emission Spectrometer. And so it's an instrument on board the spacecraft that is going to help in determining many different things. It's going to help determine chemical composition and topography for these asteroids. And so we're very excited to know this information because it could help us learn more about the early stages of the solar system. And that's exciting for everybody in astronomy, or even those not in astronomy. So keep an eye out for that. And as Rick mentioned, we have like a full moon happening. And so there's a lot of current events, and particularly we're interested in the Orionoids that are peaking. And so meteor showers happen all the time, but this one in particular happens every year around this time. And so the Orionoids are, they're going to be in peak around the 20th. And unfortunately, as Rick mentioned, because it's the Hunter's moon, the moon will be filling the night sky, so it'll be a little bit harder to see these these meteor showers. But we still encourage you to go out perhaps after 2 a.m., take a look at the sky, and before sunrise in that time. Give your eyes about 30 minutes to adjust, and then take a peek. Hopefully you'll be able to see something, but again, just keep in mind that full moon is happening. And if you're curious why we're able to see a meteor shower, or what a meteor shower is, that is when a comet enters the path that the Earth follows. And so what Earth gets to see is the leftover debris from that comet. And we call them meteor showers, and it looks like it's raining or showering. And so this meteor shower is brought to you by the constellation Orion. And Orion happens to be the constellation of the night sky where you can see this meteor shower where it happens to fall through. And so what is interesting is that Rick mentioned it's a Hunter's moon, and Orion is known as the Hunter, the famous Hunter. So that's very interesting to keep in mind as you're looking for these meteor showers. But with all that, I'm going to pass it to Alex to finish off our resources.
All right, thank you, Alicia. Yeah, we have some great resources for tonight regarding a lot for earthquakes. Our first one is the Shakeout webpage. Sorry, a lot of information about this kind of event and this day and what you can do to learn more about earthquakes. And then you also have an opentopography.org, which has a lot of topography data and tools that you can use if you're into that. You also have IRIS, which is a big institute research for seismology. So that's not just Earth, but as you can see, there's also Mars here as well. Then you can also see earthquake.usgs.gov. This is just a tracker for all the most recent earthquakes. Apparently there's some recently in Idaho. And then you also have the Southern California Earthquake Center, another resource specifically for California. And then finally, we actually have the Arizona Geological Survey from our school down south at University of Arizona, and their earthquake page. So a lot of great websites. They'll be sent out in chat. Make sure to check those out if you're looking for more information and more resources just about seismology and topology and earthquakes in general. So that's our resources of the week, and back to you, Rick.
Thank you, Alex. Hey, I have just one more poll, and I'll start to talk to you about some coming events and some things to watch for as we go. But if you could launch that last poll, sometimes we like to keep track of where people are watching from, and so. If you don't mind, if you still got some, you're still kind of engaged, and now you know how to use polls. We just want to see kind of where people are watching from. I think we know one of those people from outside the United States. I saw some things in the chat. One of our former students, Spurty, was actually sort of watching tonight, so we were thanking her for joining us. So I get it. So outside of Arizona,
guest on the panel, Rick.
What's that? Did she?
A special guest on the panel now with us tonight.
Oh, good. Spurty, are you on? Can you show us yourself? Maybe you can just tell us where you are.
I am in Pune and I'm working for India.
Oh, are you in Mumbai?
Oh no, I'm in Pune.
Oh, you are? Okay. Oh, excellent. Good for you. So it looks like more than half of us are from the Phoenix area. That makes sense, right? That's where we're located. That's where ASU is, and I'm glad you guys are joining, and I'm glad you've been participating in our program. But look at how many people are just sort of like outside of Arizona. It is the second group, and so that means our reach is going a little bit farther. We'd like to keep track of this stuff because we don't really interact with the audience as much as we'd like to. So we throw these questions in just to kind of see what you're doing and who's joining us. And I said at the very beginning of the show, and I'll say at the end of the show, Kim Baptista is going to send you a survey in a little bit, in the next day or so. It'll include some of the resources. It'll include some of the things that we've learned tonight, so that you can kind of just be reminded of some stuff to work on. But also, it's going to ask you if you have any ideas or questions or concerns or comments about the program. So please, if there's something you want to see, if there's something you like that you'd like to see more of, then that's really the time to do it, because we really organize our shows around what our audience is asking about and what you guys might be interested in. Coming up on Friday night, just 2 days from now, is what we call Earth and Space Open House. And this is actually a program that we usually do in-house again, but we're doing it virtually. And it's run by the students. It's run by grad students. And so what you will see if you join us on Friday night between 6 and 8, you're going to see a lot of just demonstrations and things that the students are working on, the things that they're interested in, some research that they're doing, some papers that they're putting together, and some of those things. And it'll be that whole expanse from geosciences to astrosciences and everything in between. So please join us for that. 2 weeks from now at this particular program on Wednesday, I think it's November 2nd, we're going to give everybody an update on the amazing James Webb Telescope, the next telescope after the Hubble Space Telescope. It's got 6 times the light gathering power. It's going to see deeper and further into space. And finally, it's going to launch on December the 18th. ASU has a lot of fingerprints associated with this particular telescope. It's a big project. We've been working on it for a long time. ASU will have visual time, seeing time. We'll have telescope time on the James Webb Telescope. You'll learn a little bit about that in a couple of weeks. We'll do that and kind of give you a sense of the night sky. We'll do a little night sky visit about things to watch for in the winter. And so that's 2 weeks from now. I really appreciate.
Rick, we have one more announcement. We have
Okay.
the Maricopa County Library.
Oh yeah. So can you do it? So I don't have it up in front of me, so I don't remember the date. Can you take it, Kim?
It is Tuesday, the 26th of October. We are partnering with the Maricopa County Library District, and we are going to be co-hosting the Universe Beyond Hubble with our postdoc Tim Carlton and undergrad Liam Nolan, and they will present the research and what they're working on as it relates to the soon-to-be launched James Webb Space Telescope.
Another James Webb. We're getting pretty excited about James Webb, and lots of activity about that, lots of learning and outreach information to the public, because that's going to be a big project. And I think everybody's going to be amazed at what this telescope can bring us, seeing deeper and deeper into our universe and way, way back in time. So that'll be fun to see. All right. I'm going to call it a close. We've gone a couple minutes afterwards, after our hour, but that happens to us sometimes. And thank everybody for joining us. I hope you're a little bit more earthquake aware, and I hope you've got something to watch for in the night sky. Check out those planets. planets, check out Venus and think about sort of that, how Venus operates in its orbit, and then what we get to see, how it actually sort of operates and how it moves through our western horizon while it's up and before it sets in December. Thank you, everybody. We'll see you in a couple of weeks, and I really appreciate your support. Bye-bye.